All right. So here we are. Unit 3 review, live stream version, whatever. All right. A couple of new things. Well, a couple of things. First of all, like usual, if you would like to ask a question, you can ask directly in the YouTube chat. If you want to use the Remind app, that's fine too. I've got the phone ready to go with the Remind ready to pop up with your questions. And good evening, by the way. So I'm doing this 2 days before the test. The test is not tomorrow. Tomorrow in class, we're going to review a little bit. I'll give you time if you want to work on the review guide, whatever. If you got questions tonight, you could ask. If you got questions tomorrow, you could ask. If you'd rather just wait until the live stream is over, you can always send questions via Remind at any time, and I'll get back to you as soon as I can. So don't wait until like late tomorrow night to study and do all this, because I don't think I'll be replying to you, after my bedtime. But we do have a test on Tuesday, not tomorrow. Just want to make sure that's clear. So I guess we can begin right away. So Unit 3 is all about two-dimensional motion, and so it involves two parts of the equation sheet. And if I could just throw this up on the screen, let's see, that's pretty much should cover it. So I just have the, it's on the screen over here. I think you could see it, yeah. So what it's going to cover is, especially for dealing with projectiles, is going to be this first box on the top left, linear motion. This is one where you'll see displacement and average velocity, and you'll have to add in x's and the y's, of course, because all these linear motion equations, the kinematics equations are called, they apply to lines whether they're vertical in the y direction or x's in the horizontal direction. So you don't see them on here because that's up to you to add them. The second part, which we kind of talked about briefly, is this 2D dynamics. This has to do with circular motion. So here's all your, everything with a little C by it. That C stands for centripetal. If you could think of it as circular, it's the same basic thing. And so all those equations that I mentioned are right here on the equation sheet. All right. So I'll leave that. So I'll just take that away for now. I could always drag it back there later if we want to. So you can see I was playing around with poles. I might try that, see how it goes. I feel like it's going to be a little on the slow side, but we'll start with this one. So I'll throw the pole up. Oh, hello. You're a little getting ahead of us here. So to answer this question here, how much does horizontal velocity, this is all about horizontal projectiles. So these are things that any projectile is an object that is affected only by gravity. So we could try this poll here and see how it goes. Go ahead and put in an answer. It should have popped up. I don't know. I tried it on myself, and this is the first time we're doing it, so we'll see how this goes. But how much does horizontal velocity affect the pull of gravity on a thrown ball? So the ball is flying through the air. How much does horizontal velocity, the sideways motion, affect the pull of gravity on a thrown ball? So is it more as the horizontal speed increases? Is there less as speed increases? Does it only affect it if there's a vertical component? Or does horizontal velocity never affect the pull of gravity? So we'll see how this pull thing goes. So just take a second. And I'm going to end it in a moment. Ooh, this thing just keeps popping up, doesn't it? All right. Well, let's see how we did. End the poll. All right. Well, the answer with 12 votes and a long delay. Let's see here. Yeah, the answer, according to everybody, is D. So that is actually correct. Horizontal velocity never affects the pull of gravity. All right. So horizontal velocity is Vx. That is velocity to the side. It doesn't really say left or right. So that's supposed to be an arrow to the left or the right. Gravity, the force of gravity pulls straight down. And so that doesn't affect how much it goes from side to side. So horizontal is the x's. Okay. I don't know if you have a system of remembering that. Some people say, well, there's a little little bar across the top that goes horizontal maybe, and like vertical, it's kind of like, looks like like vertical, vocal, like these V's are almost, I don't know, whatever system you use to remember. That's just something to keep in mind. So this one, the pole doesn't go up to F, it only goes up to D. So I was gonna have to like do this the old fashioned way, I guess. If you know the height, so these equations are directly from the equation sheet, right? And if you know the height, what equation would you use to find the time in the air? So you know the height. Which equation would you use to find the time in the air? And I can't do the poll, so I mean, if you don't want to answer, you don't have to, of course. But you know the height. So I'm just going to slowly walk you through this. The height, the dy, right? And so if you know the y's, you did the practices, right? The first practice, you did the practice. You had to do this a bajillion times because of the practice, okay? If you know the height, yeah, you guys are all right. Those who I'm seeing anyway, you got it right. You would use this one if it's a horizontal projectile. In other words, the initial velocity in the y direction is 0. That would work out. So, because remember, there's always this little caveat here. If vi is equal to 0 on the equation sheet, you can see that. Where did it go? Oh, it's over on this side. Whoop, there it is. So this is the equation if vi is equal to 0. So if viy is 0, you can use it. So that's horizontal. If it's thrown off a cliff or something like that, you can use that equation. Good. If you know the horizontal distance, what equation would you use to find the time in the air? The horizontal distance. Displacement, if you want. Technically, that's what it is. Horizontal distance, right? So that's displacement in the x direction. Okay. Well, the answer. So you know the x's, you would use this one. The reason is Vx, V average x, there's always that, because it doesn't change. So you could use, remember the horizontal velocity doesn't change as a projectile. So dx over t, and see, you might get thrown off because it doesn't quite look like that, but this is how it is on the equation sheet. And to find time, yeah. All right, so there is a delay again. I love the delay. So we multiply both sides by time, and it turns out that okay, I can't leave it like that, so I got to then, after multiplying both sides by time, I got to divide both sides by Vx, so Vx. So it turns out that time is equal to, it cancels out this, so its time is, I could use the eraser, but it takes a second. Dx divided by Vx. And like I said, 3.1 practice is you're going to be your bestest buddy to prepare for this, or just focus on that part on the review guide. That is like the bare minimum I would do. So if you find yourself finishing up the review guide for 3.1 and you're just like, oh, I'm just not quite feeling it, and you didn't finish the practice for 3.1, I would highly recommend that you complete the practice for 3.1. All right. Another question involving the linear motion equations. You know the time. So now you've got the time. What equation would you use to find the distance that something fell? Also known as the displacement. So you already know the time. What equation would you use? Again, this is just familiarity with the practice, okay, with the equations. So I'll walk you through this as you think about it. The distance something fell. All right, we got an answer. The distance something fell is dy, the displacement in the y direction. Good. All right. Yeah, so you wouldn't use this one because the problem is we don't know v average. There's no v average. The velocity, I mean, there is, but we don't know it. The velocity is always changing, right? We could figure out VF, so we wouldn't use this one because we could figure out VF. We could figure out how fast it's falling at the end, but we don't know it. And honestly, we would need a little more information because we don't know what this is. All right, it's supposed to be a question mark. The answer is C, because we want to find dy, and we know AY is negative 9.8. We found the time, and we know VIY, if it's horizontally rolling off the desk or whatever, is 0. So we'd use that. So why wouldn't we use this one? Well, again, dy is fine, but we still don't know VF. All right, we don't know VF. Y. We don't know VF in the Y direction. we could figure it out, and we kind of do that later on, but we don't know that. Once again, this one has VF, so we won't use that one. We won't use that one because we don't know VF. Remember, that's like part of the whole trick to the second part of this is when we do figure out VF, but we don't know it here. So, and for this, well, we wouldn't use this because we already found time. So the answer has to be C. All right. If you got questions about something, if I didn't explain something, if I mumbled or if I cut out or something, just let me know. I don't have 3 monitors. I can't really monitor the health of the stream. So if you're seeing something, it looks like it's good, but just, throw something up there if you got questions or whatever you need me to clarify. One more with this horizontal projectile 3.1. You know the time again. What equation would you use to find the horizontal distance? All right, the displacement in the horizontal direction. Horizontal, remember, is dx, right? For all of these, you could draw the little picture, and I'm just going to go this way for fun. It doesn't really matter which way you draw it, so it falls down this way. Dx is horizontal. Dy is the vertical displacement, and it's usually going to be, not usually, it's going to be a negative number because it falls downward. And we know Vx does not change because, as we saw in the first question, as we reminded, gravity only pulls downward, and it does not affect the horizontal speed, and the horizontal speed does not affect gravity. So they don't affect each other at all. All right, the answer is the person calling themselves Peyton, which I probably will assume it is the Peyton I know, says A. And that is actually the correct answer because the V average is the Vx because it doesn't change. The V average doesn't change. So we know that the V, whatever the V is at the top, okay, whatever the V is at the top, that doesn't change. No change. So that means Vx at the top is the V average. So whatever it is the whole time, or whatever it is at the beginning, it's going to be the speed the whole time. So V average doesn't change. We probably couldn't use letter B because here's the deal. Remember, AX is 0, which means that all of this becomes 0, which means that VF is equal to VI, and we already knew that. That's just kind of how it is. Would this work? DX, well, once again, AX is 0, so all that would go away. And honestly, believe it or not, this would work because the VIX times time is literally this equation just rearranged. So honestly, this letter C would work, but mostly you're probably used to using A just rearranged. The math is amazing. Math is great. Like this is, it does work out. This one, let's see if that one will work. Well, once again, VF plus VI divided by 2. Well, wait a minute. This VF is VI. They're the same. And so if I take the 2 and I divide it by 2, wait a minute, that's how you find an average. When you take two numbers and divide it by however many numbers there are. So this literally right here is just another way of saying V average. And well, what do you know? That's also the same as the first one. What? All right, it's crazy how this math works. And now it's the same thing. But once again, we're probably used to using just this first one because we don't have to go through all this. Like, we kind of like streamline it a little bit. Would this one work? Well, once again, no. I mean, it'd be true, but A is 0. So this whole thing would be 0, which means once again, VF squared is equal to VI squared. Okay, yeah, that's true because the VF and the VI are the same. So if it starts out at 2, it's going to end up at 2. 2 squared plus 2 squared, or 2 squared is equal to 2 squared. So, okay, yeah, this one's kind of useless. And you already know the time, so why would I even bother with that one? So technically, any of these would work, but you're probably most really familiar with A. I'm not going to do I want to save time. This is going to take an hour as it is, going by past, like literally this is The previous times I've done a review for this unit, it took an hour and 6 minutes, and they were completely different reviews. Like, and so I'm guessing it's going to take about that much time. So I'm going to not. I already have links to videos on how to actually solve those questions. I put it in the. I put a link to the whole playlist. So if you click on that playlist, you'll see a couple videos. One is horizontal projectiles in the X direction, and one is about solving them in the Y direction. So rather than me, I mean, I'll answer any questions you have. You've got a direct question. I mean, I'm not going to say, okay, can you do question 3 where I had to solve one of those? I could do that in class or something like that. But all right, so I'll be looking for that. I'm not seeing anything pop up on Remind. It's on quiet mode though, so I might miss you at first. You know what? Sometimes Remind logs me out. So while you're thinking about questions, if you have any, I'm going to just make sure I'm logged in. I am not logged in. Sorry if you've sent me any questions. Remind just logs me out of my phone every now and then. All right. Looks like I'm not seeing anything anyway, so sorry about that. Technical glitches that I should have tried out probably beforehand. Okay. Let's check out Unit 3.2. This is where I know it's not true. All right. I don't know what's behind me. So at an angle, it's a little bit different, right? In this case, I mean, we've kind of stuck with like thrown, at an angle upward. It does apply to if it's thrown downward, but the bottom line is it's not thrown. It's not a projectile that was launched horizontally. It was not thrown horizontally, right? So it's at an angle. So we've got some theta right here. That's where it's launched. So ignoring air resistance, this one we didn't really talk about too much in class, maybe briefly, but it's on the review guide, and you might have had a question about this. What angle should you throw a ball to make sure it goes the farthest? Well, to answer that question, excuse me, I have this little PhET simulation, right? And the answer is 45 degrees. Yes, exactly. So let me show you that. Now, when something's launched at an angle, I can't do, this won't let me do like straight. 0 angle. The lowest I can get is 25 degrees. I don't know if you can even see that, but I guess I could zoom in for now. Wolf. Well, it doesn't really make the text bigger, but okay. Let's keep it simple. Let's launch directly upward, right? So if I launch something directly upward, that green arrow represents the velocity, and you can see that it started out really high velocity going upward, and it ended up shrinking down to 0, and then becoming negative and downward. So if I fire that again, you could see that green vector. Maybe this will help if I zoom. Nope, because then you can't see it. And you can see, like, okay, now when I fire it at 90 degrees straight up, there is no x like component to the velocity. It's all y velocity. There is no x component. If I fire at some random angle, let's do 55, you'll see both a vertical and a horizontal component to the velocity. What you might notice is the vertical velocity changed again, because that's what happens vertically, and then the horizontal component does not change. It stays the same. Okay, and so the question is, why is 45 the best? We're ignoring air resistance, of course, but for now, in this class, I should say. The reason is the higher I throw it, let's start at 85, so it's almost 90 degrees, which means it's almost all vertical to start out with. It's a very tiny amount of velocity in the x direction, which means that even though it goes very high up in the air, it's not going very far. I'm very fast because it's not going to go very far horizontally because it's not going very fast. So if I fire that again, it spends a lot of time in the air, but it's moving like a turtle. It goes so slow. All right. The flip side is true too. If I fire it at 25 degrees, which is the lowest it'll allow me, it'll have some height. It'll have some vertical velocity, but it'll be going really fast sideways, which is great. And you would think it'd get really far, but the problem is because it's got such a small starting vertical velocity, it doesn't spend a lot of time in the air. And so because it doesn't spend a lot of time in the air, even though it's going fast horizontally, it doesn't have much time to get very far. And so as I kind of play with different angles, and you saw a diagram of this somewhere in the notes and in the practice, I think, different angles have a different combination of vertical velocity, which gives it more or less time in the air, and horizontal velocity, which means it could go farther if it has the time. So you get these like interesting combinations where like the complementary angles, like here, let me clear this out. Like 60 degrees has a combination of vertical and horizontal. So it gets kind of high up in the air, but it's not going like super duper fast. But the complementary angle, 30 degrees, has the exact opposite components. So not a lot of height, but much faster. But it's like the complete, like I said, complement. And so it goes exactly the same, because for whatever height it's missing and time in the air it's lacking, it's going that much faster. And when you get the right combination, like 45 degrees goes the farthest, because it's the best combination of vertical velocity, so it has some time in the air to actually go somewhere, and horizontal velocity, so that while it's in the air, it could go fast and far. Every other angle besides 45 has either too much height and not enough speed of a horizontal speed, or it's got faster horizontal speed but not enough height to get very far. So when you see that like a little pattern, you're just seeing all the different permutations of and combinations of vertical and horizontal, so that well, like I said, you can see it. It could get really high but not go very fast. So anyway, the answer is 45 degrees. All right, so that is the answer, 45 degrees. In fact, I'm going to go back to that slide if it'll let me. Oh, it'll let me, but this is a separate window. So the answer here is 45 degrees. I just unsuccessfully put a box around it and slightly through it. So there you go. The answer is 45 degrees. All right, let me know if that didn't make sense. Ooh, I could do a poll again. Let's see. So you read that while I do the poll. I gotta set it up again. Oh. All right, I'm not sure if I'm loving these polls, but option. Yeah, I'm not loving these polls. Oh well, it's worth a shot. We'll try it a few more times. Uh-oh, did I just cut out? Maybe. All right, I think I threw a poll up there. When is the acceleration due to gravity for projectiles not negative 9.8 meters per second squared? A, at the top of the path. B, only when it's first released. C, it's always negative 9.8 meters per second squared. Or D, it's never negative 9.8 meters per second squared. Bump. Bump. All right, let's check it out. I got a couple answers. All right, I'm going to end the poll now, which means with the delay, you already know that. All right, the answer is, hopefully you know that. Where's my little pen doohickey? All right, cool. The answer is good. Most of you got it right. So I kind of like the poll. I get like a sense. All right, between B and D, what was it? It's only when it was first released. All right, it's never 9.8. Yeah. The acceleration due to gravity always is negative 9.8. G, I mean, it's on the equation sheet. G, here, you know what? Let me just show you on the equation sheet. And it's, oh crud, I just shut it down or closed it. Let me just reopen the equation sheet. There it is. So now I can't see anything. All right, there it is. Always 9.8. It's there twice because it got the two different units, which are basically the same unit, but it's there twice anyway. And so yeah, 9.8. Now it says 9.8. Why is it negative? Well, remember, what does the negative mean? It's downward. So it's downward, and so that's why we use the negative. Negative is downward. So yes, it is always negative 9.8 meters per second squared. That is a very common test question. Okay, it's meant to. I hate to like put it this way, but it's not meant to trick you, but it's meant to like see if you're overthinking this or underthinking it. Okay, just remember the acceleration due to gravity. Acceleration due to gravity is always negative 9.8. Even as you're sitting there right now, it's always negative 9.8. Okay, on Earth. All right. At what point is the vertical velocity of a projectile 0? All right, let me throw up another poll. It just takes me like I can't set up a default like poll. I have to actually like do A, B, C, D every single time, but I like it. I kind of like it. It's kind of a pain, but it's a little slow too, but that's okay. So at what point is the vertical velocity of a projectile 0? A, at the top of the path. B, only when it's first released. C, it's always 0. Or D, it's never 0. Vertical velocity this time. Vertical velocity. Vertical velocity. Don't overthink it. Okay, what is vertical velocity? V, Y, right? V, Y. You've drawn it. You just saw a whole, like a little simulation of it. Okay, so let me just, well, you know, I'll leave it up there. Why not? You know, clear that away. Clear that away. Vertical velocity being the vertical one, right? The up and down one. Look at, oh, it's getting smaller, 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 small. Oh no, oh, yeah, it's 0. And now it's getting bigger again, except negatively. Where was it 0? Where was it 0? Well, I guess I should have ended the poll, but now you know. Now you know. The answer, of course, is at the top of the path. Did I end the poll? I ended the poll. Oh, good. All right. Good. Most of you got that one right. Although that's a 37% of you said the wrong thing. It's always 0. Ooh, no. All right. So the 37% of you, they got it wrong. Did you see what I mean? Okay. Pause a second on questions like, look at this question and this question. I mean, they look, at what point, when is the acceleration of gravity? I mean, there's basically one word that's different. I mean, it's phrased slightly differently, but there's one operative word, one key word that's different. Well, term, I guess. Like in question 7, I asked, when is the acceleration due to gravity not negative 9.8? And in this one, I kind of, okay, it's the same basic question, but now I'm asking about something else. The first one was about acceleration. This one's about vertical velocity. So it's a quick question, right? Make sure you take a second and actually like define the terms in your head. All right. Always make sure that you are sure, reasonably sure that you're that you've got the terms defined in your head. Make sure put it simply, make sure you're answering the question that's actually being asked, not the question that your brain made you think that it's asking. You know what I mean? Like, so make sure you know what the question is asking. Vertical velocity. If Newton's first laws are always in motion, why is 0 at the top? Great question. Newton's law. Okay. Newton's law. It's Newton's inertia. Newton's first law. An object in motion will stay in motion. And then there's the second part. Unless acted on by an unbalanced force, right? Unbalanced force. Well, what's the unbalanced force acting on it? Okay, that is a fantastic question. So look at side to side, the horizontal, there is no unbalanced force, right? There's no gravity pulling on it, so that doesn't change. So Newton's first law holds true there, all right? But for the vertical component, there is an unbalanced force acting on it. Gravity is always pulling it down. It's unbalanced. There's nothing to counteract that balance while it's in the air, which, yeah. Motion is in the X. There's no unbalanced force, but in the Y direction, there is an unbalanced force. And so the motion does change. All right. And that's why in physics, we got to think of them as separate. All right. We tend to, and rightly so, like I said, we think of it like this. It's like that we, in our brain, which is what we're seeing, this is the velocity. It's like up and down, right? But in physics, to understand this mathematically, objectively, we got to look at it this way, right? Forces only occur, let me phrase that. They occur in many directions, but it's helpful and useful to us to mathematically look at them in their different components, in their horizontal and vertical. And remember, they don't affect each other, which is why it's important that we separate them out. Gravity only pulls downward, but this thing is also moving to the right, where nothing is pulling on it or pushing on it. I mean, I could add air resistance, but even that, you wouldn't even notice much of a difference. Just enough that I don't want to confuse anybody. Okay. Hopefully that answered your question. That was a great question, honestly. All right. If the horizontal velocity, if the horizontal velocity of a projectile is 2.4 meters per second, what is the horizontal velocity 0.5 seconds later? So while it's in the air before it hits the ground. So I don't know if I could draw right on here. So 1/1000. So maybe like right here. I don't know. Well, yeah, it's a little bit quick, but somewhere in this range. If the horizontal velocity of a projectile is 2.4 meters per second, what is the horizontal velocity 0.5 seconds later? So horizontal velocity, Vx, right? And I just got done saying, I just showed you in that simulation, the x component, the horizontal one, there's nothing affecting it. So the answer, and I'm expecting it to pop up in the chat in a minute, but I mean, if anybody wanted to put it in there, but it's 2.4 meters per second. It doesn't change. All right, there's no forces. Ax, I'm gonna put this in parentheses, is equal to 0. There is no acceleration in the x direction. It looks like a T. I really should not write so sloppily in a review session. So let's try that again. Ax is equal to 0. There is no force in the x direction, so there's no change. All right. If I'd ask about vertical velocity, then we need a lot more information about that. Actually, I think we could probably figure it out. But we would have to do a little bit of math in there because the gravity changes things. But in this case, there is nothing. Throw questions out there if you got them. I'm just trying to give you general terms. So I know you might have like specific questions, or maybe you don't yet, but you might have specific questions that you're not sure of. Please ask. If it has to do with the review and you think it could wait till tomorrow or whatever, that's fine too. But I'm trying to give you like a general mindset right now and just things to think about and way to go into reviewing for this test and actually taking the test on Tuesday. This is too much I can't do this many things. So we're just going to do this, like I said, the old-fashioned way again. When calculating time for a projectile that initial velocity, which equation should you use? And I just want to clarify, we are launched at an angle, okay? Which means that the initial velocity in the y direction, let's make this, does not equal 0, okay? So we can't use that one equation. I guess I should, clarify if vi is equal to 0, right, for this last one. So right away, I'm just going to eliminate that one. We just can't use that one. All right. We can't find, that's the whole point of all this. If you've done a few of these questions, these are the questions where I gave you 10 and you only had to do the evens or the odds. But if you want to do like the whole thing, you could do all 10 for extra credit. So if you remember, all right. Calculating initial to time for a projectile that initial velocity. All right, hey, this is good. You know what? Technically, you're right. Let's put it this way. All right, okay. Here, you are correct. If we're talking, if you know Vx. Okay. My question was poorly worded. My apologies. Good. How about if you know initial velocity what if you know initial velocity in the y direction? So great. Yes, you are correct. So I'm going to just circle this whole thing because that is correct if you know. Okay, so there's two different ways. If you know Vx, What if you know v initial velocity in the y direction? In other words, you've done the whole calculation, you know velocity is this thing, and you did the blah, 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 which we're going to get into in a moment. You did the angle thing, and this is what you know, VIY. You know the side of that triangle, right? All right, now the question gets a little bit more difficult. We said E, so let's eliminate that one. Well, because we're trying to find time, right? And guess what? There is no time in E, so that can't even be it. I mean, I guess you could like go roundabout and maybe find it, but yeah. You know, initial velocity. Let's go with D. Maybe D. Okay, maybe. And well, you could find time, but you don't know D. D's not given to you, so we don't know D. So we don't know displacement, so yeah, it's not gonna work. And so same thing for, we don't also know over here, right? So we don't know dx. It says, it doesn't say. Maybe this question is pretty asked kind of poorly, but yes, the answer is B. This is a question mark, by the way. The reason it's not C is because, and again, the question maybe was worded poorly, so I apologize about that. We don't know the displacement in the y direction. We know the initial velocity. We know VIY. And if we know VIY, so I could put VIY, right? We already know AY. Okay, good. And time is what we're trying to find, so we're gonna have to rearrange. That's fine. Hopefully we're used to it. But the question is, do we know VFY? And here's the thing. If you remember, okay, I thought I got something else. FY is equal to negative VIY. Okay, that is a thing. That's going to be the case. The reason is because if something is launched, it goes all the way up and all the way down. Then whatever speed it goes up with, the initial velocity vertical, like if you're looking at this little triangle over here, it's going to come down with the exact same speed, vertically speaking. It's going to come down with the exact same speed. And so VFY is equal to negative VIY, the opposite. And so if you know VIY, man, this question was worded pretty poorly. But if you know VIY and it goes all the way up and all the way down, you know VFY. So the answer is B. Okay, so I hope that was less confusing than it. I hope that was helpful to you. I guess I'll put it that way. I wish I would have worded the question a little bit better, but hopefully you understand what I was trying to get. And if not, just let me know. I'll try to clarify a little bit better. Okay. This one I really wanted to make 4 choices and I could do the poll, but well, I couldn't. I liked all the options and I wanted to leave all the options in there. What is the final vertical velocity of a projectile like the one in the animation? Final vertical velocity. All right. I kind of sort of answered it previously, except none of those are the option, right? I said, well, if you look here in this little triangle, right? This diagonal is V, which means that over here is VY. That's the initial velocity in the Y direction. That's X. We're not really concerned about X. That doesn't change. So I said that, it's not right to say, let's go VFY is equal to negative VIY because it comes down with the exact same speed. In every situation, it's going to be the answer here. And if you need to refigure it out, then the angle here, this would be the opposite side, this would be the adjacent side. All right, if you know the little pneumatic device, I think it's the pneumatic device, SOHCAHTOA. All right, I didn't actually teach this, but it goes it'd be nice if I could actually say it. SOHCAHTOA is like the trick, right? And so if you're looking for a little trick, just remember sine goes with opposite, cosine goes with adjacent, which means that we have the opposite. We're looking for the opposite side here, which means it's going to have to be the sine one. And since we want the final vertical velocity, we want negative which means that the answer is B. Now, if I over-explained that and you were good with your system you were using before, I apologize. But maybe seeing why it's this helps you. Okay, so V times cosine of theta will give you VYI. Negative V times cosine of theta is negative V Y final. Okay. This would give you Vx if you're, which you also need to know. Letter D is, you don't even need it. It's like, how fast is it going backwards? Which this, you don't need it. And 0 is not the answer. So, okay. So I think that last explanation is probably helpful, hopefully helpful to you to see where we're going with this. Like, this is how you solve for the initial velocity in the y direction. This is how you solve for the final velocity. It's just the opposite. You're going to just get the opposite number. Why is it negative? Fantastic question. When it's going up, it's positive. When it's going down, it's negative. That's it. No other explanation. That's simply the answer. So, do you need negative V cosine theta? Probably not, because you've probably already solved VIY by taking the positive of it, and you just need to take the negative of the number. So, but negative indicates that it's going downward. So like I said, up here, it starts out, the initial velocity is positive, and down here, the final velocity is negative. Vertical velocity. Okay, so that's why it's negative. Okay, I'll leave that up a moment. Now you're probably wondering, wait, this is like all these problems you could work out. Yeah, I know. I thought about that again. Look at it, it's already 7:42, right? And this is one of those things, like, if you want me to explain something to you, I gladly will. And I just don't want to make a 2-hour review session. I mean, I could, but I feel like it'd be helpful to some, but I don't know how helpful it would be in the long run to everybody. So I wanted to be the most helpful to the most people. So I sort of made that executive decision to not work through a problem. I feel like I did enough of those in class, and I have some videos. I should add that the video the video in the playlist is okay. It's from 2015 though, and like I said in class, I need to redo it, and I just haven't had a chance yet, so I apologize. So I recorded myself second period a couple days ago, and then I put that link on the OneNote, right? See OneNote note for a good video, for a video on solving these problems. Okay. I don't want to, I guess I could pull it up right now. Can I? OneNote. Let's see what this looks like. I don't have it even open. So I'm not going to open it right now. So go to the OneNote, go to 3.2, right? It's chapter 3.2, unit 3.2, and look for the video of me explaining it during class. Okay, it's a kind of a low quality. I'm not super happy with it, but I mean, like, it's not on my usual YouTube channel. It's just on the school's YouTube channel for my school account. But I think it's better than the 2015 video that I made. So, or just message me or ask me in class. Okay. I'm not seeing any questions, so I'm going to move on to circular motion. But if you want to ask me a question, throw it up there. Circular motion. I combine these two units, 3.3 and 3.4, because 3.3 is more again, this is a sort of bookkeeping stuff. It's not necessary for you to know this, but 3.3 is more conceptual, and 3.4 uses the math. Okay, so that's why I combine them together, because I don't see the purpose in separating them too much, just for the sake of separating them. So, question, you're sitting near the center of a merry-go-round and your friend is sitting near the edge. Ooh, I could put this in a thingy, so I'm going to do that. Who has the greater rotational speed? So, is it A or B or C? Who has the greater rotational speed? You do at the center, near the center, and your friend near the edge. So you got a circle. It's a merry-go-round. There's the pole. So this is A. That's you sitting there near you're sitting near the center. I could read, right? It's okay. The pole kind of like takes away something. So takes away a little time. So here's the center. So you are sitting near the center. The merry-go-round is going, right? Your friend, letter B, is sitting at the edge. All right. C basically says you're going the same, right? You're going the same speed. And I got some reminds with the answer. And the answer is, think about it this way. I'm just gonna tell you, it's not C. You're both not going at the same, rotational speed. Yeah, no, I apologize. I'm wrong. I should not have crossed that out. Where'd my little eraser go? It's rotational speed. And so because it's rotational speed, that's like RPMs. It's like how fast you go. It's not linear speed. It's not like who's got the fastest speedometer. Rotational speed is just how many times you spin around and go around in a circle every minute or every second, right? RPMs. And the answer is when you go around once, your friend also goes around once in the same amount of time. Okay, you have the same rotational speed. Ooh, I could end the poll. Oh, everybody's gonna hear it right now. I have a bad poll here. End poll. All right. Maybe I ended it quick enough because of the delay. But bottom line is, yeah, because of that, you both have the same rotational speed. All right, same rotational speed. All right. Most of you answered with letter B. That's a different question. That's hang on, I outdid myself here. I'm going to erase all of this because I knew I can't draw very well. And take a look. All right, I already had a drawing here. You both have the same rotational speed. And again, this just has to do with like the definition of what rotational speed is. So make sure you're familiar with rotational speed versus not versus linear speed or circular speed. We'll call it circular speed. Centripetal speed. What I call it in the notes, tangential speed. All right, not tan. Why did I do this to myself? Nope, I totally spelled it wrong. This I doesn't belong there. Speed. Okay, so it's not tangential speed. It's rotational speed. That I doesn't go there. Okay. Tangential speed is if you had a speedometer who was going the fastest. You're sitting in the middle, you're not going to really feel much speed compared to the person on the outside, but you're going to go around at the same amount of time. So once again, rotational speed means you're going to go around once and your friend is going to spin around once and you're going to go around at the same time at the same rotational speed. To contrast that, which one of you has the greater linear speed? All right, let me just throw the poll up there because I hope you all know the answer now. I kind of explained it just now, but I'm going to just, see who gets the right answers right now. Okay, now that was rotational speed. Now we're talking linear speed. So who has the greater linear speed, you or your buddy? Linear speed. There's the poll. I guess I'll take this moment to take a sip of water. So here I'll make a note, not rotational speed. Okay, I'm going to end the poll because I feel like if you're paying attention, you got it. All right, let's see how we did. Well, the answer is your friend does. Come on, poll. There it is. Yes. Wait. Yes. There we go. Good. Yeah. The answer is your friend does. You have your friend. Here's the deal. Linear speed. When we go back to like the other stuff, velocity is distance over time, right? Speed is distance over time. Okay. When it comes to linear speed, what we call the circular speed or centripetal speed, it's the same basic idea. It's still distance over time. But instead of time, it's the period. All right. In other words, you have the same period. You're both going around the circle in the same amount of time. You have the same rotational speed. It takes you the same amount of time to complete a circle. Okay, like I said in the previous question, as you go around once, it takes you a certain amount of time. Your friend goes around once, whoa, hopefully they stay on the thing. They complete the circle in the same amount of time. You're stuck together on this merry-go-round. So the period is the same, but what's different? It's that distance, all right? It's that distance. And if you remember, well, if you remember the equation, it's 2 pi r is on the top of the fraction. Why? Because circumference of a circle is 2 pi r. Why does that matter? Well, because the circumference of a circle is the distance you're traveling, 2 pi r. In other words, you have a much smaller circle to travel. You're traveling a much smaller distance because your circle's smaller. Your friend is traveling a much bigger circle, which means they're traveling a much greater distance in the same amount of time. All right, which means that they're going to have a greater speed. It doesn't really matter. Think of it conceptually in this way. If you're sitting close to the center of a merry-go-round, you're not going to feel like you're spinning much at all. You're going to just kind of see the world turn around you. It's going to be kind of fun, I guess. But if you really want to feel the speed, you got to sit on the outside of that thing, all right? You're just going to feel like you're going faster on the outside. What is linear speed again? No problem. This is why we're doing this. You ask these questions. Linear speed is just literally you're traveling in a straight line. That's linear speed, all right? It's just in circles. When we talk about circles, we're talking about there's several reasons that we use a slightly different equation. Is because that we're no longer moving in a line. We're moving in a curve. Okay, so one of the reasons that we call it something else is because we take into account that you're moving in a circle. So we use circumference instead of trying to like measure the distance that way. So linear speed is just how fast you're going in a straight line. Centripetal speed, tangential speed. What else? There's a couple different ways to call it. It's just you're moving in a circle. All right. It also has to do with the fact that you're moving in 2 dimensions, which we're not going to get too far into right now. Okay. Next question. What will happen if the centripetal force acting on an object disappears? Okay. In other words, you're moving in a circle and suddenly you lose the friction. You're trying to run or bike or drive in a circle and you hit a patch of slippery stuff and there's no longer any friction to push you into a circle. Yes to the reminder I just got. If somebody is traveling a greater distance in the same amount of time, that means you're going faster. Yes. Yes. Mm-hmm. To this question, if the sun just suddenly disappeared, and the sun is the thing causing the Earth to go around it, the gravity of the sun is causing the Earth to turn in a circle, what will happen to the Earth? If you're spinning an object around your head, like on a rope or a string, like I was in class, and the string suddenly snaps, what's going to happen? Okay. So will everything continue as it was? Will the object fly straight outward from the circle? Will the object fly away tangent to the circle? Or will the object fly toward the center of the circle and eventually stop? I'm going to end the poll. What's an example of an internal-external axis? Good question. I'll answer that in a moment. Let me end the poll so that we can see the question that was just asked. And I'm going to answer this question first. Yeah. So if you want to just memorize the answer to this, the answer is C, as some of you said. 25% you got it right. Yeah. So straight out from the circle is the wrong answer, right? So something's flying out around in a circle and the string breaks or whatever. It's just gonna, you're saying it's gonna just fly out like that. Okay. Think about what's going on. The thing is traveling in a circle, right? And the string breaks, the force disappears. Would it fly directly out from the center of the circle? Or, as the correct answer is, if something is traveling around in a circle and it's doing that, all of a sudden the string breaks or whatever, will it continue on in the direction it was going the moment that the force disappeared, the string broke or whatever, the sun disappeared? All right. Now, quick math term: if you got a circle and I have a line that touches the circle in exactly one spot, that's called a tangent. Okay, that's the definition of a tangent. So just remember this word tangent. Okay, just like if you want to just be practical and just memorize stuff, that's the idea here. So if you think about it, flying straight outward from the circle, and like I said in class, that's kind of what it seems like is happening. Like if you're just like flinging something around and just you let go, it feels like it's going to go straight out. But like I mentioned, at least one student talked to me about roping and, you know, what do you call it? Twirling a lasso around your head. When you throw the lasso, it goes out from the side. It doesn't go straight out from you. Which, like I said, if you think about this doesn't really make much sense. If something is traveling around in a circle, let's say I let it go here. I mean, would it make sense that it just suddenly takes a 90-degree turn and flies out directly from the circle? No. But that's what we think, because we don't really, I mean, like I said, why would we even think about that? That's kind of what it seems like happens, but that's not what happens. This is what happens. So if the velocity is in a circle and all of a sudden the force disappears, it's like it just keeps moving in a straight line, going back to Newton's first law. Okay? So just remember that. If it just disappears. Okay. I think I just saw a question. I saw a question on Remind. I want to make sure I address it. I think I just addressed it. In the meantime, what is an example of an internal external axis? An example, huh? Okay, I think I answered the ones on Remind. So an example. An internal axis is something like a wheel. All right, so an internal, the simplest example is a wheel. All right, some kind of wheel. I'm drawing way too many spokes here, but you get the idea. So, all right, I think you just did. So if we have a wheel, the internal axis is right in the middle there. It's spinning around itself. So the wheel itself is spinning, and so that is rotating, right? So going back to rotate, that's rotating. An external example, man, what's a good one of that? Well, you don't see them a lot. I don't think I've got anything in my room here. Something that's moving in a circle that's got an external axis. So I don't know, like let's say the only example is like here's somebody here in the middle, right? And they're swinging something around in a loop. Okay, they've got something on a string. Good question. I'll answer that in a moment. Okay, and they've got like some object here on a string, and there's like a little tiny string. Okay, they're holding it right here, and so the object here is revolving around some like internal axis or external axis. The axis itself is not part of the object. The axis that this thing is spinning around is outside of the object. That's revolving. Okay, my high quality drawings here. So in this case of the wheel, the whole wheel, the axis is part of the wheel. In this case, where somebody's spinning a whatever around in a loop, the axis is the sun revolving around the earth being examined. Yes, the sun revolving. So if you got the sun, okay, and it's like, here's the sun, here's the earth, okay, here's like the continents and all that. Right, so that's actually, I don't know why I didn't like use that as an example. So the earth is revolving around the sun, okay? The axis is the sun, or there's actually an axis sort of inside, but we'll get, I mean, it's whatever. We'll just think of the sun as the axis. It's not part of the earth. It's revolving. Okay? Great question, diabetoglucose, or great answer. Great question, Peyton. Okay, couple more. Running around a circular track at a constant speed. Are you accelerating? I don't even know if this is worth throwing up as a poll, but I'm going to. Here. No, I don't want that option. Are you accelerating? Yes or no? Running around a circular track at a constant speed. Okay. Circular track though. Are you accelerating? There's the poll. I'll give you like 5 seconds. Oh no. My streak of 1 hour and 6 minutes is going to be broken. All right, end poll. Answer is yes. Why? Because your velocity is always changing. Your velocity is always changing. Therefore, oh no, that's okay. What? Wow. All right. Acceleration means, so I guess I'll spend it. Can you explain? Yeah, I'm going to. Person who just sent me that reminder to explain acceleration again, you're on top of things. So acceleration means, remember that symbol? That's the change in velocity. Okay, that little triangle means change in. So acceleration means change in velocity. Okay, velocity, velocity is your speed, which is not changing if you're running at a constant speed, and direction. Holy cow. Speed and direction. So if you're running around in a circle, it's your direction that's changing, okay? And if you're running around in a circle, you have to constantly be pushing yourself into a circle, because otherwise you would just naturally run in a straight line. If you've ever run in a really tight circle, you can feel your body trying to fling you. It feels like you're being flung outward. You're not, but you feel like you definitely had to push yourself into a circle. If you ride a bike or drive a car, you had to force yourself to go into a circle. There has to be friction involved. In other words, there has to be a unbalanced force, and we call that the centripetal force. And whenever there's an unbalanced force, that causes an acceleration. Okay, so the bottom line is velocity is speed and direction. If either one of those changes, you have an acceleration happening. What causes acceleration? An unbalanced force, right? So that's what, so acceleration is a change in velocity. Velocity is speed and direction. If you're running around in a circle, you're changing direction, even if you're at a constant speed. So does that clarify? Hopefully that clarifies things. All right. Next question. Almost done. Only a couple more. And I'm going to throw the poll up right away so that it's there. So that's what I'm doing. So next question is, and I think this is the second to last one. If the moon travels around the Earth 4 times in 109.288 days, seems oddly specific because that's legit actually the thing. What is its period? Huh? Great. I'm glad that helped. What is its period? So I'm going to go, so period is the capital T. And if you look on the equation sheet, period, where it's not even there, Mr. Chern. I know. This thing can use a little work, I suppose. If you go to the back of it, under waves, believe it or not, there's the equation for period. If I remember, I'll put it up on the screen for the test because it's on the back and it's easy to forget. Because why is it under waves? Well, we'll find out when we talk about waves. And for whatever reason, we didn't want to include it twice, right? So because it has to do with, well, whatever. Time divided by number of cycles. That's the period. So if we're talking what is the period of the Earth, we need to know the time and we need to know the cycles. Okay, so the time is this many days. Okay, but there's a problem, and I'll get to that in a second. So 109, we'll just, for this, okay, days. The cycles is 4. It goes 4 times. That's what cycles is all about, how many, whatever the cycles. Okay, the problem is if you put that in your calculator, you're not going to get the right answer. And the reason is the choices are all in seconds. And so we need to do a little calculations here. And so this gets a little tricky. It's like, all right, well, 109 days, 8 days. All right, I'm just going to do a little math here. If it comes down to it, well, we'll work through this. We need to change that into seconds. So the best way to do that, and days, I don't know how many seconds are in a day, but I do know how many hours are in a day. There's 24 hours in one day, right? So that's going to cancel out. I'll be left with hours. All right. I don't know how many seconds are in an hour, but I do know how many minutes are in an hour. So I know that there's 60 minutes in 1 hour. And some of you guys are getting really concerned right now, like, wait, what's going on? Okay, so that's that's hours we cancel. I'll be left with minutes. And now I know that there's 60 seconds in 1 minute. And so minutes will cancel. I'll be left with seconds. All right. So I'm going to close the voting. That way I could see what the answers you guys put are. I need my screen back. So when I do all that, I get my answer of, it's C because, okay, all right, it's good thought. The problem is, so then when I do that, that comes out to being basically 9,44248, 3.2 seconds in 109 days. If I take that and divide it by 4, all that to get A. All right, now that was kind of complicated. Yeah, that was kind of complicated. Needlessly so, some might say. But I just want to show you that just pay attention to a couple things. Where did the, no, you're not. Oops, the poll. I swear there was a little bit more said, but I missed it. Maybe you were able to delete that. Maybe I'm wrong. Yeah, so the bottom line is you take the time divided by the cycles. Just make sure that the time matches up. I don't think there's anything like this complicated on the test. I would hope not. Oh, I remember the question on the, I don't remember exactly how many questions are on the test. I'll tell you tomorrow in class. I think there was 32. I don't hold me to that though. I honestly don't remember for exactly. Okay, bottom line is it is time divided by cycles. It goes around the Earth 4 times. That's how many it cycles. Okay, and the time is the time. All right, last question. Once again, there's no poll because I've got 5 options. What is the direction of centripetal force acting on a revolving object? Tangent to the sun. These letters match up with the picture. So A, tangent to the circle. B, a combination of inward and in the direction of motion. Look at B. So kind of inward, but also like in the direction of motion. C, inward directly toward the center. D, outward. Or E, a combination of outward and tangent. All right, there's no poll, so just think about it, and if you're brave, put it in. So thank you, Peyton DM. Or if you're not brave and you're just feeling like, hey, I'm just gonna put an answer in, and you're like, I'm not brave, but I'm gonna act brave. Dry water says E, okay. Person on Remind says C. All right, I'll put you guys out of your misery. Ooh, it's not C because it's not revolving. Interesting. Well, okay, hang on. Diabetes, glucose. It is okay. So the question does say it's revolving. I'm not sure where you got. Hopefully the question wasn't super clear. This little arrow here tries to indicate that it is revolving, whatever the object is. So if it wasn't revolving, there wouldn't be a force. We could just say it that way. The answer is always, always, always inward, directly toward the center. If you thought anything else, you may have been overthinking it or underthinking it. But the bottom line is the centripetal force is always, centripetal force by definition is always toward the center of the circle. Always. Okay? Always. 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 Dry water, you're a little late to the party, probably because of the delay, so I apologize. It's a good one. It's a good one. All right. So, centripetal force is always toward the center. I can come back to that, but I just want to ask if there's any questions that I can answer right now. You'll be able to ask me tomorrow in class. You could always ask me via Remind, of course. I highly recommend you do that review guide. Check out the key along with, I think the questions are worked out somewhere. Do the practices, watch the videos, and you should be good. Okay. So, Unit 3. Are there any questions for me? You got about 15 seconds to ask. Otherwise, I don't have much more to say. Oh, I could say we're not going to switch seats. This unit was what, 2 weeks? I'm not going to have you sit in your seat for 2 weeks. I'm not sure what that means. I hope it's a good thing, but I hope it's a good thing. All right, well, then I will just say, reiterate, do the study guide, do the review guide, work through it. I know you can do this. Remember, there's multiple choice, but there's going to be an FRQ part where you have to answer some of these questions. And please reach out to me, reach out to somebody. There's physics tutoring is on Wednesdays, so you won't be able to do that after school, but maybe start thinking about that. No, we're not switching seats for this unit. Because like I said, we only were in these seats for like 2 weeks or less, and there's not only, after Thanksgiving break, there's not going to be that many weeks either. So yeah, I know. Don't worry, Omar. Everything will be completely different second semester. There'll be new people in the room maybe and everything. I don't even know. So yeah, okay. We good? Hope you guys enjoy the last few hours of your weekend for real. It's nice and windy out and blustery, and stay warm. So the next unit, there's one more unit. It has to do with momentum. If it will involve eggs being dropped from a distance, and hopefully not splattering. That's one of the things in the next units. And will we ever be able to pick our own seats? That is a possibility. I have not quite. That'll happen later. Not this semester. I'll just say that. Okay, not this semester. Partly because we're not switching seats again this semester. It's already done. All right. Well, you all have a wonderful, wonderful evening, and I'll see you tomorrow. All right. Take care.